Hi everyone, and today we'll have a very interesting discussion on this model known as SayCan. Right, the long name is Do As I Can, Not As I Say. So this was great work done by a lot of people at Google Robotics. And the main aim of this work is whether or not we can key in a natural language input, like a free-form text. Like, for example, you can ask the robot, can you help me get a Pepsi can? Or it can be something even more indirect. I just worked out, I'm thirsty. Can you get me something? And then the robot would kind of interpret it in a human language kind of way. And after that comes up with a series of actions whereby it helps to fulfill whatever you ask the robot to do. So it is a very flexible system in the sense that you don't have to constrain to the traditional like fixed inputs and outputs. Like right now, if I want to, like, for example, ask the vending machine to give me like a can, I kind of need to press the button of that particular can, and then the can comes out of the vending machine, right? So it's very fixed and structured. But if we can use like some form of NLP, we would be able to generate the requests in a more user-friendly way. So instead of pressing the button on the vending machine, I can just say, I would like something non-sweet and something that is able to help me be more energetic. So then maybe the vending machine would come out with a coffee, a black coffee or something like that. Yeah. So rather than you pressing that input button and constraining yourself, you let the language model decide what best fits your outcome or best fits your goals. And then the model is able to produce a set of like actions that can generate the intended goal. So I chose this paper because in the fast and slow architecture that I was trying to do, there's actually this part of goal planning to fulfill a goal. And what better way to fulfill a goal than to use an NLP approach, which is really very impressive these days. So let's begin right now. So this is the key question we like to ask ourselves here. So the question is, can we use a large language model to just directly predict like maybe a sequence of actions, or more directly, just the next action given like a particular state? So like the state that the robot is in is given by the sensory inputs, which can be video, audio. It could even be like past states, past memory, or this can also be part of the input here. Or it can even be memory of past examples. You can put this kind of stuff here as well. Yeah. So the idea is, can you give, based on this sensory inputs, also the past actions? This is actually part of the memory that I was talking about earlier, the past actions, and given a certain goal state that you want to be in. So this is something like your objective that you want the robot to do. Like just now in the earlier example, you want the robot to give you maybe a non-sweet energy drink, like maybe a black coffee, you know, that kind of thing. This is an objective. Can a system given just this over here, you can pass through one of the most powerful things right now. Everyone's talking about transformers now because of ChatGPT. But before ChatGPT actually is used in a lot of other things as well. And one of them is in planning for reinforcement learning. So can we feed into one of the very powerful architectures known as a transformer or large language model, and outputs and action? Okay, so this is a very interesting question because, you know, the large language model is able to do things like association. You know, you have the query key value. You can actually do like cosine similarity to find out relevance of like query to the current states. Yeah, so this is all of this makes a large language model very enticing to use in order to map like a particular series or sequence of events in the past in order to predict something in the future. So because of all this association, and you can do it through multiple layers, like in a transformer, because you have multiple layers as well, each of them have self-attention of the previous layer, you can actually do very complex hierarchies of associations. So the key thing is, can we just use an LLM to directly predict the action? Okay, so let's just do a quick poll. Who thinks that in order to fulfill the goal? Yeah, Any takers? Who thinks that we can just use a transformer model, give it all the inputs we want, and then out comes the action that will give us the goal? Okay, so Jerry says yes. How about the rest? Do you think this just using the LLM, a large language model, is already sufficient?
I say
Okay.
yes, but I think with some catch.
Okay, yeah. What's the catch?
Catch is hard to model uncertainty.
Okay. So uncertainty as in the uncertainty of the state.
Uncertainty as in how do you trade off things like exploration, exploitation?
Ah, yes. Okay. So of course that's a very relevant point. A transformer doesn't do like really exploit. It just matches the matches the highest probability output given its input. So it may not do the like suboptimal move or action just to explore the environment. So this is a very important part because this is also one of the reasons why in SayCan, the action chosen is not meant to do explore exploit. It's just meant to do a particular action that is already pre-trained. So we don't have to train the RL component of it. What we are doing is we have a set of skills and we have a set of trained skills. And then we just choose one of them to perform. Yeah. So this is more like a higher level planner whereby you have a few skills, like for example, skill A, skill B, skill C, skill D. Like skill A could be like taking a brick and putting in another place. Yeah, that's skill A. Skill B can be like navigating the robot. Yeah, so all these are already pre-trained over millions or billions of examples using the very inefficient reinforcement learning or other methods. Already pre-trained, all you need to do is to select the right kind of module. I call it module. Yeah, so it's like modular construct. The right kind of module in terms of the skills that you need, or rather the right kind of modular skill in order to fulfill your goal. So this is actually a more meta level planner where we are given a goal and then we choose trained skills in a sequence in order to fulfill this goal. Yeah. So the exploit part doesn't really concern the outcome here because we don't really need the exploit to train the RL policy. Yeah, does that answer the question? Sorry. Okay.
I think we can discuss later.
Yeah, sure. All right, let's move on. So this is the video. Let's take a look. Okay, so this is quite cool. This is a kitchen robot, it's called Everyday Robots. And like it has some camera, like so you can like ask the robot to type in something in plain language. And then what the model would do is they will predict the next action that the robot should do by a large language model. Okay, there's also this part called affordance. You can see over here. Later I'll explain what this is. So the LLM will predict like one of the most likely actions. And then the affordance would also tell it what to do. Okay, so you can see it's executing a sequence of actions right now. Put down the Coke can, find the sponge, okay, because you need to clean. So sponge is an item that can help to clean. The large language model has decided that it can help. Okay, pick up the sponge. Go to the table because the spill is at the table. Okay, but you see this part, it cannot clean by itself. The human still helps to clean it. Okay, so this is not end-to-end, it's not fully done. Okay, but the idea is quite cool. The idea is that you have a human-based prompt and the robot can plan a sequence of actions in order to fulfill that aim or that goal. And it can be very, very long horizon actions. So, okay, let's go. All right, so let's come to the problem of what this might have. Okay, the large language model is very versatile. As you know, ChatGPT can answer quite a lot of questions, okay, but it also tends to hallucinate, also tends to output wrong answers, which actually sound very convincing also. So it's the same thing for this SayCan. Because you are using a large language model, it can output stuff that actually doesn't really like make sense. So for example, if you say, I spilled my drink, can you help? So like for example, GPT, very helpful. Okay, like it's trying to say that, oh, you spilled something, maybe you can try using maybe a vacuum cleaner. I guess vacuum cleaner is like for dirt, but there's some kind of vacuum cleaner that can help to do with like liquids as well. All right. Lambda is like asking like, do you want me to help you find something? Yeah. So this is like more like chatbot kind of stuff. Doesn't really help you offer you the advice, like trying to help you to solve it. Flan is very funny. Flan is saying, I'm sorry, I didn't mean to spill it. I mean, you can see that this doesn't really link here. Flan is actually an instructional model where basically it's trained with various instructions and like premise and premise and outcome. Yeah, so those kind of things kind of bias the kind of language that the language model output. But the main thing that you can see over here is that these three different models, okay, all of them are not grounded in real world context. Okay, because if we just give them a sentence like this, okay, they don't really have the like robot sensors or kind of environment cues to tell you what exactly the robot can do. So this is purely text-based. So a large language model that only has the text modality can only tell you what the next words might be that has the highest probability based on your input prompt here. Okay, it doesn't really know whether or not there's a vacuum cleaner in the world. It doesn't even know like whether or not like who spilled it. Okay, who spilled it, maybe you can encode it in text. But you see, Flan didn't get the meaning. Okay, it thought it spilled it. All right. So sometimes you may not want it to recommend you an option. Sometimes what you want it to do is to tell you the solution. So like maybe, you know, some kinds of output may not be the kind of output that you want. So like here, you find a cleaner, not really. Maybe you just want to know like what I can do to clean up. I don't need to call a cleaner to clean up, you know, that kind of thing. So this is something that is a problem with large language models. Large language models are very versatile, but they lack understanding of the real world and what is feasible and what is not. So the authors of this paper initially wanted to just use large language models, but soon there were problems in the sense that large language models don't exactly produce the right actions or produce feasible actions that can be done. So then how can we solve this? All right, these are some of the solutions. Okay, so the first solution is quite obvious. In order to make sure your actions are the kinds that you want, okay, limit the output to be only the possible actions that the agent can do, like the robot can do. If the robot can clean, then the robot should like limit the actions to like maybe scrubbing or wiping, that kind of stuff. You don't ask the robot to, you know, do a break dance when, you know, it's not possible by the agent. So this agent will inform the model what are the possible actions, and the model just chooses the best possible action based on what the agent can do, right? How then can we do like planning to reach the goal state, right? Because we have like a start state, and then we want to reach the goal state. So this actually looks very, very similar to those kind of look-ahead planning problems. So one way to do this will be like, even if you use the AlphaGo, AlphaZero approach, you do a tree search here of possible actions, then you do a look ahead, and then eventually one of them might reach the goal state. Okay, but they did not do this in this work. Okay, this is actually quite, this is actually a very important point. All right, in order to do like planning, and you want to do like this kind of AlphaGo, AlphaZero approaches, you will need an accurate simulation, because you need to kind of look ahead what will happen in the next few steps. So this actually can be hard in the real world. So in the real world, you may not know like how exactly your action will impact. Like you want to pick up a Coke can, you may not know how the Coke can might be in the next time step. So AlphaGo, AlphaZero works very well in a very constrained environment that you already know like what are the possible interactions. Or if you don't know the possible interactions, you are able to do self-play in order to find out the transitions, like for example, mu0. But I mean, I've done a research with these methods, and I find that they take very, very long to train. So this SayCan did not use this kind of method, but instead what they did was that they heuristically determine what is like the best possible value of the next action. In terms of the heuristic, what kind of heuristics they use is an LLM scoring method, and also a value scoring method. This is from the RL value function. So using this two of them, they kind of scored all the potential actions that the robot can do. And one part of it, the large language model will tell you like how relevant it is to solving the goal. And the reinforcement learning value function will tell you like how feasible this action is. So they only did a one-step look ahead, and they just choose the best action based on that one-step look ahead. Yeah, also because there might be infinite amount of actions, and then, you know, if you do a look ahead with tree search, you may not converge that well. Yeah, so there are practical problems with doing tree search-based methods. Okay, so we can talk more about it in the discussion later. So this method is just a one-step look ahead using some form of scoring system, using two branches of scoring. One is for more contextual based, which is the large language model, and the other is the more feasibility based, which is the reinforcement learning value function. Okay, so let's see this thing here. So this is like the prompt here. I spilled my drink, can you help? Okay, the language model will basically like identify which are, okay, this is a bit fast. So let's highlight again. So the language model finds out like this, like cleaner, vacuum. The affordance says sponge. Okay, so in the end, when you combine both together, you will find a more feasible outcome, which is the sponge. Okay, because the rest, the cleaner and the vacuum, are not in the environment. You can see here, there's no cleaner, there's no vacuum. All right. So that is why if we have another way to like bias the language models, it might actually help you to get more effective solutions than just using the language model itself. Okay. So this is the overall flow, right? So the first thing is a goal-directed language model. So this is the goal, okay? Or this, actually, they call it the instruction. But in my language, I like to call it the goal, okay? Because that's the goal of what you want to do. You can put the apple on the table. So in order to put the apple on the table, what you do is then you prompt the language model. It's quite interesting. You don't actually have a separate architecture for this. You actually just prompt the language model to like fill in the next step. So over here, the next step is I would something. So what the language model will do, this is actually later I will describe more. This is actually like the log probability of like how likely the LLM would predict these few tokens. And in this case, the lower, the better, like -6 or -4. -4 is the best. So the language models will rate all these actions. All these actions are fixed actions based on the robot, based on the agent's abilities and the objects in the scene. So these are all fixed. You need to run through each and every action. So this doesn't really scale very well, see? So if let's say you have like 10, let's say you have 100 actions and you have 100 objects, you need a total of 10,000 okay, not 100 actions, 100 views, and then do on 100 objects. You need to evaluate this on 10,000 actions. Okay, so this is one of the problems of scaling up. Okay, you will have difficulty scaling up because it's an exponential increase in the number of evaluations you need to do here. Okay, but let's say we have a limited set of skills. We can actually do this LLM score here quite easily. Okay, and after that, you also need to ground this with some form of like ground truth, whether the robot can do it. So this will be the affordances with value functions. And over here, these are the value functions that are used for this robot. And this robot, basically, this value function is the Q value for each of the states here. So the Q value of the state is a proxy to how feasible the action is. Okay, because the Q value in this environment is given as a like 0 or 1 as the end reward for this environment. 1 is when you fulfill the task and 0 is you don't. So in some sense, the actions here, if you do it over multiple simulations, the scores here for the Q value would be sort of the average Q value of the action achieving the task. So if it kind of achieves the task, this value here will be closer to 1. And if it doesn't achieve the task, okay, it doesn't achieve the goal, then this will be more or less like going to 0. So you can see that given this state of like picture here, the Q value will have the states and you have the action. So the action is called Li. Okay, your state and the action here, you can get a Q value here, which tells you how feasible the action is at achieving the current task, right? And also is grounded by the state as well. So you can see the language model wants to pick up the apple, but there's no apple to pick up. Okay, in the scene here, you don't see an apple anywhere. There's no apple anywhere. So the value function tells the language model, okay, you don't have an apple here. You need to go and find an apple. Okay, or you can go to the counter or go to the table. Okay, this is also one of the things that can help to achieve the goal. Okay, but you kind of need the apple first. Okay, so both the instruction relevance here and the task affordance, after you multiply them together, okay, over here, you also multiply this by an exponential probability. So it's like e to the power of -6. In the end, you do something like that. So after that, you take this multiplied by this value here to get the final value when you combine them together. Okay, and the one with the highest value would be the one that you choose, which in this case is the apple. Okay, so after we find the apple, we can then keep looping this multiple times. Okay, this is the interesting part. You can actually use the large language model to do sequential planning. Okay, because after you've select your first action, you can put the action as part of the prompt. Interesting, right? You can use the action as part of the prompt. So this would mean that it's predicting the next action here. Okay, and you can keep doing that until you reach result, which in this case for the SayCan model is signaled by this end word here is called done. Yeah, as long as you predict done, you will end the rollout. So it's very cool. You only need to roll out one action per time step, but you can keep putting all the predictions as part of it, and then you can keep generating the next action. So this whole process will be repeated each time step until you reach termination. Okay, any questions so far on this? I thought this is a very cool thing because it uses the flexibility of language models.
So, hello?
Okay, over here, they use value functions. Yes.
So does author formulate this this process as an MVP? And do you think it's appropriate to formulate as an MDP?
Markov decision process, is it? This whole thing?
Yes.
Yeah, I think you can formulate this as MDP. Yeah, because it's like each action that you do, you modify the environment. And then after that, you can take the change environment and then you can generate again. So as you can see that at each step here, when you do it, okay, not only you feed in the LLM to this updated prompt, the world state has changed also. So like, for example, find an apple, I found it. So then the next stage, you can like pick up the apple. So there's some form of transition here, although it is not as clear cut as a normal MDP because the potential states can be infinite. Yeah, because the real world may not have a repeat state due to like lighting conditions or placement of objects and so on. So it's similar to MDP, but it may not be mathematically derivable.
My concern is more on, by nature, the large language model is trained in the auto-regressive manner. That's my concern. So
large language model in auto, or you mean to predict the next token, is it? Like
so
those kind
the most straightforward way to formulate is every new output is conditioned on all your history instead of just your current history.
Yeah, you mean all the history as in all the past episodes, is it?
As in your entire,
or just the past action?
The condition on your in this case, your new action is
all the trajectories.
Yes.
All the previous trajectories, right?
Yes. So is that a big problem? I'm just thinking about it. It might not be a big problem. I'm just thinking. I'm not sure.
No, I don't think so, because when you can condition on all the past actions, right? You kind of already like have a way to do like prediction based on past states. It is very similar to a language model where you predict the next word, right?
I think I know because here, like for language model, your action space is I think almost infinite, right? How large is the action space? If you think of it as an agent, very large, right?
Yeah, the action space can be very large, but in the SayCan model, they constrain the action space to like pick and place tasks, navigation tasks, so that it's feasible to use this method.
My main concern is if they want to formulate as MDP, then your state space is very large.
Yes,
It's
correct.
combinatorial large, right? So
Indeed.
but I
No,
guess
but I'm saying that this,
my hunch is I think large language model can deal with that kind of problem. So it may not be a very big issue here.
and that's why the LLM is so flexible, because the state space that it can encompass is actually infinite as well, because the combinations can express a variety of states. Okay, it's just whether the robot can understand that.
I guess
This one I will discuss later. This is a very interesting question. Actually, there's some questions in the chat. How is the value determined? All right. So since you all asked about this, actually there's a slide on it. Let me just zoom into the slide on the state value. There we go. Yeah, this is how the value function was trained. All right. So I'd like to highlight that this process is highly inefficient. You just take a look at this amount of chips that they use: 100 hours, 3,000 CPU workers to collect, and 3,000 to train the target. So this highlights actually like the point that I was making, the fast and slow, is that learning a value function is very inefficient. Okay, here they use a temporal difference learning, whereby they train the Q function of the previous state to match the one-step look-ahead value. Okay, I don't have the equation here, but I just want to highlight that it's temporal difference learning, that you learn this and you backpropagate from a successful episode. So there's a lot of target errors here, because sometimes the action you perform might be correct, but because of the later action, it will be incorrect. Yeah, so you may learn the wrong stuff from this temporal difference learning, and you will take very long to converge, which is more or less explains what is over here. And somehow they use a sparse reward. So this value function is actually not the best function that you can use, because I feel like RL using value functions is a very inefficient process. So I just wonder why they didn't use more efficient stuff like actor critic, which actually uses a policy network as well, and also the value function, when they update the actor critic, they update all the trajectories at one go, all the previous states at one go, compared to temporal difference learning. So there are some things that could be improved here to make the learning better. But one thing for sure is I kind of disagree with using value methods for reinforcement learning because of the slowness of learning. But suppose, for example, it converges, all right, then this value function will be a good proxy of how well, given this particular state, this state is here in this 3D space, sorry, not 3D space, 2D, two-dimensional space, but got color, so it's three-dimensional. Action, the action that we take is given by this like vectors. The vectors can be like the rotation, the vector, which is like the coordinate vector of where your gripper is. Yeah. Okay. There's also another, like, this is also a state. Yeah. So this state is like where would I be next, and so on. So this is the image state, and this is the up here. This is the image that the robot has, and all these are the robotic arm vectors. Yeah, like it's actually quite a complicated problem to actually train the gripper. Okay, because the gripper has like 6 degrees of freedom, the arm and everything. You need to kind of train all this, which is not included in this training time here, by the way. The gripper arm probably takes billions or gillions of episodes to learn that 6 degree of freedom. This is just roll out of the train arm just to collect episodes for your value function. So this amount of training time here is just to train the value function, not to train the robot. The robot is even worse to train that robot. Yeah, so you can see how inefficient reinforcement learning is. Okay, but today we are not going to like talk about how inefficient the robot takes to train. What I want to focus on today is how we can use this idea of language models and some groundedness in order to improve decision making, sequential decision making. So yeah, this is how the Q value function is learned. It's learned using the sparse reward of 0 or 1, where 1 is when the sequence of actions has successfully learned or successfully solved the goal. All right. Yeah. Did that answer the question? I mean, there were two people asking this, Jayaram and Christina. Yeah. Is that all right? Yeah. So basically, an encoding of the state space, the action space, and of course, this is the skill space. Like what skill I do, or like in this case, like do I pick up the can or something like that? So each of the different like actions that the robot takes here, okay, would actually be encoded for in this like skill. And then with each skill, you can actually predict like whether or not this skill, given this particular state space and action space. So it's actually very, very complicated. There's also a skill space here. So this is the action, the state. Okay, actually, I'm starting to think that this S and A is best to interpret it, okay, as the state of the robot. Okay, I mean, you can consider this all the state of the robot, because the action is technically given as the skill here. This is more like the traditional action in RL, because the skill description kind of tells you what action to do. Okay, at least the more meta. This A here is more like the micro action of the how the gripper should be. But if you are looking at the meta plane, like a high level plane, this skill description is your action. And then all the like rotation of your arm, all these are the states. So maybe you can reconfigure this as like action and state. Yeah, so to make it easier. Yeah, but in terms of the robot, the action of the robot at the micro level will be like whether the gripper is open or closed, that kind, or rotation. Yeah, those are the micro level action. But now we are now the CEO. Okay, we don't care about how the robot gripper moves. Okay, those are our workers down there. We are looking at more like the broad level planning. Okay, where should you go? Where should you invest next? What sector to invest in? That kind of stuff. We are planning at a higher level right now. So this value function best interpreted as these are the states. S and A are the states of the robot, and this L prime is the action, the skill that you are using. And you just keep training this over like a lot of episodes, and hopefully the value function converges. And as you will see in the next few diagrams, it actually doesn't really converge that well. Okay, so there's some room for improvement here. Okay, any questions on the value function training here? Okay, let's go back to the start. Okay, where was my slide? There we go. Okay, so this is the key idea. As what I said, the language is the flexible part. It helps to do the goal directedness. This value function is about how feasible your action is. Actually, if you think about it, because your Q value is linked to whether you complete the episode or not, this value function is also can be related to the goal direct, some form of goal directedness also. Because if you can fulfill the goal, you get an episode reward of 1. If you cannot, then you get an episode reward of 0. So the Q function here is in some sense about like whether or not you can do the action. Because if your state doesn't have like an apple, of course you cannot find of course you cannot pick up an apple, right? Because it won't lead you to the goal. But this has some form of like which action can help to attain the goal as well, based on the robot's point of view. Right? And then over here, these are all the pre-trained policies. Okay, can you imagine using reinforcement learning to learn these skills and to imagine? Yeah, it is probably not practical. Okay, because reinforcement learning is so erratic, the targets keep moving. If you train this whole system end to end, it will probably collapse. That's why this is very important. These are all pre-trained. Okay, this is very, very important. Okay, because RL is so inefficient. If you pre-train them in a modular way, you can use these modules at a higher level in order to fulfill much more complex goals. So this is a key insight with this system as well. Some skills, like for example, in humans, like the skill of reading, the skill of walking, those can be trained in a modular manner. And then like what the brain does is maybe it can mix and match different skills to solve different tasks at a more meta level. And that is exactly what this paper is trying to do. We are planning at a meta level. I find idea, right? Referring to meta as the word all right, not the company. Okay, so this is what exactly I was talking about here. This is prediction at the meta level, where instead of predicting like I'm a student or something, like a token here, like in a transformer architecture, you have a set of like inputs here, and then you want to predict what's the next output token. Like I am a, then you predict like student or something like that. Yeah, based on the context. Okay, over here, what we are trying to do is we are trying to predict the next action based on the like goal. So over here, we already give it some goal, and then you try to predict what's the next action given this goal. Okay, this is really interesting. And these actions are constrained. Okay, they are not arbitrary actions. They are actions that the robot can actually do. All right, so we already predefined some set of actions already. So these are some example tasks of the SayCan architecture. So the first one is the human gives it like, I spilled my Coke, can you bring me something to clean up? All right, so first, the robot sees no sponge here. So although like, okay, the language model says find a sponge. Okay, so it got it right. All right. And you can see this is the value method. Can you see that the value method, all of them look about the same? Go to trash can, find Coke can, go to table, all looks about the same, right? So the value function isn't exactly the value function, not very well trained. Yeah, so so this is something that definitely can be improved. And I would like to bet that the value function trained by temporal difference learning doesn't converge. It didn't converge. That's why you see here, the longer the bar is, the higher the value. So it didn't really converge. You can see that even like go to the trash can is high value here when there's, okay, maybe like, clean up can be considered like, throw away something. Yeah, so yeah, this is something that doesn't really show like that this value here is trained correctly, because everything here is correct. Even like water bottle is correct. So yeah, but luckily it found the correct option. Next, like pick up the sponge. So the language model also predicted it correctly. Pick up the sponge is correct. Okay, but over here you can see that this value function here is very low. Okay, so this kind of means that there's very low affordance, and luckily for this case, the language model outweighs it and it does it correctly. Same thing for here, and then done. Yeah, so the language model seems to be, just from this example alone, it seems to be powering a lot of the decisions that needs to be made. Okay, because the affordance, it's not very high, like especially for actions that actually would be feasible and actually go to the goal as well. Okay, let's look at the next task. So here is a very similar task, but instead of clean up, can you bring me a replacement? So same thing, first find a Coke can. All right. Okay, but instead of like cleaning up the Coke can, what we'll do is we'll need to pick it up, bring the Coke can to the user, and then after that, done. Yeah. So this again highlights that the language model is like driving most of the action, because if we look at the language model here, the language model itself can already do the job. Like it already has the highest probability here. All right. Then now we look at the next example. This next example shows like how the affordance can actually queue the actions. So this is a case whereby the language model itself fails. All right. So look at here. How would you put the sponge on the close counter? So the first action is, of course, you need to find the sponge, because there's no sponge here. We need to find where the sponge is. Okay. But the language model pick up the sponge as the main thing. Okay, but luckily the affordance here is almost negligible, like zero, close to zero, which means that it's not possible to pick up a sponge here. So in this case, the value function here is trained nicely, okay, because this action doesn't really work. Okay, but if you look at the previous case here, like over here, like pick up the, okay, there's no pickup. I guess over here they didn't have the pickup thing, so maybe all these are all feasible in the value functions. Okay, but you can see that here the value function, the pickup is not feasible. So at least this means that the robot is telling the large language model, there's no sponge here, I can't pick it up. Yeah, so this is the case whereby the value function actually plays a role in grounding the model to make sure that the option is feasible. So instead of doing the pick up the sponge, the model instead chooses find a sponge. Oops. And that's exactly what is done here. And then the rest, you can see that the language model actually picks up the right approach at the first go. So from these 3 tasks, again, I also did some experiments with the SayCan model that's on, I did it on Colab. Okay, I hope I can show you, okay, because OpenAI, the API suddenly crashed on me just now right before we started this. But what I found out is also that the language model actually drives the majority of the tasks. So if your language model is good enough, okay, the language model can actually plan the sequence of actions quite well. Okay. So this is the algorithm for SayCan.
Sorry, one question.
Go ahead.
For the first case, since the output from language model is sequential, right? So why would you say the second one is not feasible? I don't understand.
You're talking about this find the sponge, pick up the sponge, is it? Are you talking about this picture here?
Yes.
Okay, so you can see that the longer the bar means the more probable it is. So the language model actually predicted pick up the sponge because this is a higher length than the.
I thought the output is on your left. On the left is the all 5, right?
Sorry, what do you mean by the output is all 5?
On the left, you have 5 actions to take, and it seems in sequence, right? Follow an order.
Oh, you mean this 5 actions here?
Yes. Yes.
Yeah, actually, when you predict the first action, the first action, all these are actually empty. So the first action is I would, then you put like number 1, and then you put a blank, and then this will be predicted by this model here. Yeah. So there's
only have one outcome, one prediction.
Yes, for every state you do 1 prediction. So after you finish your first state here, then over here will be like 1, find a sponge, then 2, blank, 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 blank. Yeah. Then your language model will then predict what's the next action here, and then your value method will take this picture here along with like the gripper position and everything, and it will predict the value function.
But you do have the value for all 5 action, right? Even for the first one.
Sorry.
For the first scenario, you do have find a sponge, pick up a sponge, go to close counter. You all have all the 5 action.
Yeah, actually it's more than 5. They're just showing like the top 5 here.
So that means you already have the first action, find a sponge, right?
Yes, correct. So all these actions are pre-programmed already in the robot. Like find a sponge, pick up a sponge. All these are the axiomatic actions.
So these are not generated by.
These are not generated by. So the thing is, all this over here, in order for this SayCan model to work, all these actions here must be already pre-trained. So all these are already given to the language model. What the language model is doing is, given this outcome, find an apple. So for example, so actually I have a slide to talk about it, but since you asked, I will talk about it here. So like find an apple. So for example, the probability of prediction of find given like the previous times probability of n given the previous chunk of words, and probability of apple given the previous chunk of words. So the model is like sort of, you're forcing the LLM to predict that token. And then at every single token, okay, it may not be words, but over here for simplicity is words. For every single token, you are trying to find out the probability of that token being predicted, okay, given the previous set of words here, like given all this set of words. Then you repeat that for the next token and the next token, so on, until you reach the end of the entire list of tokens you put inside the language model.
If that's the case, why you have the confidence over all actions? If the language model only give you 1 outcome.
Oh, the language model gives you an outcome for each action. So you do this process for find an apple. Then you have find the code also, right? So you
no, I'm talking about the previous one, still the first scenario.
Okay. Yeah. Okay, let me just write this first. Okay. So yeah, I mean, since I'm talking about this here, I'd like to also say that instead of using a probability and multiplying like that, which might make it very small. Okay, so yeah, answer the question later. But since I'm talking about this, I'll just talk about this. I will just continue this. So if you were to do like probabilities, it might be very small. What we can do is we can just use log. Okay, so because when we do like log of this times 0.1 times 0.1, so the log probability, okay, when you do log, actually they did ln because they multiply e to the power or something later. So when you do this, you can actually, because of the properties of ln, you can actually do an addition like that. So later on, there will be a slide saying that these probabilities are actually the sum of log probabilities. So this is actually the reason why instead of multiplying very small numbers, we just add up together negative numbers like that. Okay, yes, sorry, back to your point. Sorry, what was the question you want to ask again?
Can you back to just now the slide?
Okay. This one, yes.
Yeah, still this the first case. So if the language model only give you one output, why do you have this language, the blue color bars over all the action?
Oh, okay. So the language model only gives you mean this language bar, right? The blue color one, right?
Yes.
For each action, the language model will give you a score, like the probability of each. So for example, the first one, maybe the log probability is like -5, -4. Then maybe the second one, the log probability is -20. Is the opposite. Okay, because the larger the bar means the higher the probability. Okay, so maybe I write it in terms of probability. So maybe this probability is 0.8. I mean, and this probability is maybe like 0.3. So actually we do a normalized probability, making the probability that is the highest become 1, and then the rest will scale up accordingly. So you can see that each of these actions will be given a probability based on like how probable they are, ranked by the language model, and it's also a relative ranking because everything, the lowest probability will be scaled back up to 1. Yeah.
Okay, but then why is the output of language model condition on your image as input?
No, the language model is only text.
Then why is this prediction different for different scenario you have here?
Oh, because when the first action is predicted, the language model will see everything here in pink.
I see.
So based on just this context alone, like how do you put the sponge on the closed counter? The first thing that the language model actually predicted is to pick up the sponge. Okay.
Regardless of what environment.
Regardless of what the state of the robot is.
I see.
Yeah, that's why actually initially the Google robotics researchers wanted to just use language model, but they realized the language model doesn't really reflect like what is feasible on the ground. And that's why this grounding in terms of affordances came in.
But I would argue that this language model itself already is not good enough, because if it does have an action of find the sponge, why would it pick up the sponge before find the sponge? So I think this language model itself is not really good, right?
Yeah, I guess you could put it that way, but in another way of thinking about it, the language model does not know whether or not the robot has a sponge or not. So maybe the language model thinks that, it has already reached it. But of course, you can say that you can cater for all contingencies. So we just assume that we don't have anything, and then we plan accordingly, right? Yeah, so maybe with more training examples, the language model would automatically find the sponge first.
But you already specified all the action, right? So the language model knows all the actions in the action space with respect to find the sponge. Yeah, so it's not like it didn't has any prior. It knows it's supposed to pick from all these set of actions. Yet pick up before find. Then I still feel like this language model itself is not good.
But if you look at how it was phrased here, look at this. How would you put the sponge on the closed counter? So I mean, if I don't give you the image, you just shut your eyes, you don't look at the image. If I ask you a question, how will you put the sponge on the counter? You would kind of assume that you have the sponge already, right? Because I'm asking you, how will you put this sponge? You know what I mean? Like, it's sort of implied that you have the sponge by the phrasing of this question.
So is it purposely misleading question, is it?
It's a misleading question.
Okay, yes.
But you know, sometimes these misleading questions can happen in real life as well. Like a user input, you can't constrain his input, you see?
Okay.
Yeah. So in cases like this, the feasibility state of the robot given by the affordances would then be the case of like differentiating whether or not the particular action is good or not. Like over here, you can see this kind of cues the model to tell it that, you know, you shouldn't do this action.
I see. Okay.
Yeah. Okay. So I'm glad that's clear. So that's why there's a need for both of them. But I think this affordance could be done better. All right. We can discuss more about this later towards the end. So this is the overall algorithm. The algorithm, actually, I more or less talk to you all in a non-code manner. But if you want to make it more clear, you have like an instruction I, which is basically your goal. This instruction is your goal. All right. The goal state that you want to do. A current state that you have right now. Okay. The state is like the state of the world, the image, and also it also includes the robot arm vectors like grip, you know, rotation, that kind of thing. Set of skills, okay, the set of skills and their language descriptions. So this language description like can be like pick up the sponge. So what we do is we start off with nothing, okay, and then at every state, okay, as long as the language model doesn't predict done, all right, what we do is we find out the LLM scoring, like what's the probability that I will output this. So for example, the LLM can tell me what's the probability of outputting find a sponge, okay, given the query, okay, and like over here, you also condition against all other instructions. Okay, that's because, you know, we also need to like given the, okay, maybe I don't put query, I put like goal or instruction. Yeah. So you kind of need to know all these probabilities. And then let's say this probability is 0.5 and this probability is 0.1. Okay. So assuming these are the only two actions, you know, we don't want to make them small. So we kind of scale the top probability to 1 and the rest will follow suit. So this is like multiply by 2. So that's why over here there's a condition on all the rest of the instructions as well. Not because the language model actually conditioned on all the previous few skills. Okay, it's not like that. What will happen is instead you just predict the log probabilities for this few token predictions. And then once you have a list of log probabilities of each of the different actions or each of the different skills, you just scale it up accordingly. That's why it conditions on the rest here also. Okay, then we have this affordance here. This affordance is basically like given the state, which is like your image and your robot arm, you know, kind of stuff. Okay, and also given like a particular skill. So this is actually the queue function. Okay, in the SayCan model, this is actually the queue function of like your given state and your your action. Okay, action is given by the skill here. Okay, so this is basically like what see over here. This is basically like probability of like success of following this skill and action. So this is given by the queue function. Right, this is a binary. CPy is a binary kind of variable to predict whether or not, you know, you will succeed given this action. Okay, so what you do is you then multiply them together. Okay, and at the end of it, you then just choose. Okay, you choose the skill that gives you the highest probability of the LLM multiplied by the affordance. Okay, this is very complicated. Okay, you actually don't have to know all this. Okay, but I just thought for completeness, we should go through this. Okay, so after we execute this in the environment, okay, we get a new state from the environment, Sn+1, which is like the new robot arm state, the new video state. And then you go back again to the start here, and then you use the large language model to predict the next action. So it's a one-step prediction, but you keep doing it until you predict the skill as a done skill. Okay, just to highlight later, I will be showing you the pick place environment. In the pick place environment, they actually didn't use the Q value here. What they did was they used this thing called the VLID, which is some video detection with some context. So basically, this will tell you whether or not objects are in the scene, like whether there's a yellow box, whether there's a yellow block, yellow bow, and so on. If the object is in the scene, okay, we give it a value of 1. 1 if it's in the scene, and 0 if it's not. Yeah, so this basically means that if the object is in the scene, okay, it's a feasible action. If the object is not in the scene, it's not feasible. So that's similar to like blanking out certain actions and only choosing some actions. Okay, they also did something like 0.2 if it's a done action, which means that they don't want to make the done action happen too often. So you multiply the done action by 0.2 in terms of the affordance. So this is the demo that they gave in the pick place. They did this method instead of a Q value. Okay, because there's no RL policy for the pick place environment. So this shows that you can use other things to do the affordances as long as it makes sense. So in general, what you need to take note of when you do the affordance is like this. This is the general rule for the affordance. High value if action feasible, low value if action not feasible. Okay, that's all. You don't have to follow the RL method. As long as you follow these principles, you can design your affordances accordingly in this manner. Okay, that's a lot of things on this slide. You have any questions on this?
For me, I have one question, or maybe
yeah,
two, because I actually missed
please
a huge portion of what.
Hi,
Chong-Ming. I missed quite a huge portion
hi.
of what you talk about. I came late, so I'm so sorry. So I'm not very sure what affordance means here. So in a nutshell, maybe can you just summarize what is affordance? Sorry about that.
Yeah. No, affordance is this part. So if the task is feasible, the affordance will be high. If the task is not feasible, it's using a Q value, reinforcement learning. So if the Q value is high, it means that that certain action or that certain skill can fulfill the goal.
So the set of inputs are the actions.
So
you get the state and action.
Yeah, correct. So the value function is, so I don't want to go through the details, but it is if that particular instruction, and in some sense, this Q function will then be a proxy to whether the action is feasible in the current state. Because if it's not feasible, then it will have a value of like close to 0 because it doesn't reach the goal.
Okay. Okay, I see. Kind of partially answers my second question, which was actually about error propagation. Because if you only have the large language model, right, I could imagine that there will be error propagation in the sense that once you take a wrong action, then the error will propagate and the actions that it takes downstream will become even more wrong and wrong after a while. But I guess this can be kind of mitigated by this affordance function thing.
As long as it has some relation to like attaining the goal, your affordance can also tell your language model, hey, you are wrong.
Yeah, the affordance is kind of correcting the language model as well, right? Because only the correct set of language inputs will be used as the instruction for the next state, and that will be fed into the language model itself as well, right?
Yeah, correct.
Okay, got it. Okay, thanks.
So the action is a joint selection between the LLM and the affordance. So both of them will guide each other. It's like two different heads. One of them saying like, oh, I'm using the text inputs. This is my understanding of what's next. And then you have another person says, hey, I'm the robot itself. Based on my sensory states, this is what should be next. They just combine them together in a weighted manner. In this case, they just multiply the probabilities together. And then you just choose the action based on what their combined discussion is. You can treat us as like two people in the room talking to each other. Yeah.
Okay, got it. Thanks. By the way, you have.
So actually, this is linked to the next part. I'm not talking about this in this set of slides, but Socratic models is like a follow-up of this, where they actually have video language model input, text language model input, and you also have chain of thought. Yeah, so they actually have different ways to like let different modalities talk to each other and then come up with a joint decision. I personally think the Socratic model is too complicated, so I'm not going to cover it. But if you're interested, go and Google Socratic models, because that is the kind of model whereby they have different input streams and each of them can talk to each other to like advise each other, and in the end you have a joint decision. Yeah, the idea is cool. Okay, although I think this will be very complicated to program. There's too many things already. There should be a more elegant way than the Socratic models. Yeah, but this is related to the idea of like two different heads talking to each other. Yep. Okay, let's move on. Okay, so this I will skip because I already talked about it. Like, in order to find out whether the token is well predicted by the LLM, you just take the sum of log probabilities. And then if the LLM predicts the action, okay, the sum of log probabilities will be lower, which means there's a higher probability that the LLM will actually predict the action. Or in this case, the action here is actually the instruction, okay? The instruction of, oh, sorry, it's actually the skill. Okay, let's not confuse. The instruction is the goal in their paper. So over here, this is actually the skill, like go pick up the sponge, find the sponge. So it's a very interesting way of using the LLM to actually do the prediction. So how is the affordance like? Affordance is the feasibility of performing the action. Okay, it's using the Q value in the paper. Okay, but it can also be heuristically encoded. Just now I described a way to do the affordance function, which is using the like VLID. Okay, this VLID is basically to find out whether objects in scene, and then you just give it a score of 1 if object is in scene, 0 otherwise. Yeah, so this is a very crude way of saying that if the object is not in the scene, you cannot do anything with it. Yeah, so this doesn't work too well if you have partial observability, but if you have full observability of the environment, you can use something like that. The VLID can be something as simple as, okay, over there in the paper is actually RCNNs, region proportional networks, or you can even use like stuff like YOLO, you know, that kind of stuff. You can also, as long as you can like classify whether or not that bounding box contains a certain object or some segmentation contains an object, you know, you can use that kind of tool in order to do your affordance. Otherwise, some other things I can think of to like do affordance is you have a sort of maybe database of like commonly occurring images, and then you just map like maybe in the latent space, you map the L2 distance. If the L2 distance is great, or you can just use the L2 distance as some metric in terms of like whether or not a particular state is correct or not, depending on your database. Yeah, so there's various ways to do affordance functions. And yeah, I'm not going to limit like our idea of this affordance function. I don't really think the affordance function is good. I don't think this is good. Okay, so the idea of this affordance function is good. Okay, so we just learn from the idea. We don't learn from what they did in this paper. Okay, so now I'll go through the code walkthrough for pick and place. Pick and place is basically a method. It's an environment where they have a robotic arm gripper. They call it the UR5 gripper. And they have this table of objects here, like randomly created. Stuff like pick up the green block and place it on the top left corner. So this is actually trained using this model called clipot. Okay, so this uses clip embeddings, okay, to actually encode the text, okay, into the action of the robot itself. And they actually use another model called the transporter model, which is some series of REST nets that can do like rotational equivariance. So you can actually rotate the object. So you just see one instance of an object, you can do it for any rotation. So if you're interested, you can check out this tool also. I'm not going to cover in detail due to the lack of time, but these are the key ideas. They already use a pre-trained model. So this is a pre-trained model. And what the GPT, or rather what the, what do you call it? SayCan, what SayCan is doing is given like the instruction, and the instruction is this one: put all blocks in different corners. Okay, given the instruction, what it will do is basically do this few, it's like generating code. Like these are the 4 actions that we need to do. And then the action number 1 will then be given to this clipot model. And this will be the instruction to the clipot model. So the clipot model will take in this like language phrase as the instruction, and then it generates the like action of the arm moving from one place to another place. Yeah. So this is an example of like a very like meta level system. So this is the meta planner, where split the goal into sub goals. So this is exactly the kind of architecture that I was looking for my fast and slow. That's why I'm covering this today. So this is an idea of how we can use natural language processing to plan sub-goals. Like the aim is to put the blocks in different corners, and then we get the 4 different sub-goals here, which can be executed by a lower level algorithm. Okay, so all this clipboard, transporter model, all this is not important. Okay, this basically just means lower level model. Okay, you have a lower level model that does like the groundwork. Like if you have a zoom board, your robot can move forward. Your robot can turn left, turn right. You know, those kind of stuff that can do the execution for that. Those are at the lower level. Okay, but what I'm really interested is like, for example, if your meta goal is to travel from point A to point B, then like how your wheels move or this, you can just tell the lower level model, I want to move 1 square forward, I want to move 2 square forward. And then you can just use like a NLP approach to plan out all your different actions. And then the zoom board will then move accordingly. Yeah, so this is the key idea. And let us see the code. Okay, so I'm going to stop my share of the screen and I'm going to share with you the code itself. Okay, so oh no, okay, there's something in the chat. All right, so let's see. Christina asks, is it possible that all possible actions will be calculated with probabilities? Yes, this one I believe I answered already. So all the actions will be calculated with the probabilities by the language model and the affordances. Yeah. Okay, so I unfortunately don't think I can run the code anymore. Okay, because the session is over. But let me just, oh, looks like I can run it. Okay, let me see that it can work. Yeah, so I was playing around with this. Okay, so unfortunately the thing has overran the time. But let me just highlight what is happening here. So this is the robot pick place that is given in the demo of SayCan. So this is the system of this pick and place. So they use this thing called clipboard. Okay, the exact details of how to get it is at the top. Okay, I'm not going to go through. What I'm going to focus on is how SayCan works. So how SayCan works is like that. Okay, so clipboard, this one is basically the low-level algorithm to do a particular action, like put the green block into the green bowl. You can actually configure here into different things, and then you can run it accordingly. Unfortunately, my runtime is over, so I can't show you. Okay, but I'll put this code here, and then you can just run it like on the link or something. Yeah, I'll put it on the YouTube link. Okay, because I actually changed some of the code here. Okay, so this is the LLM scoring part. They actually use an open API, open AI API call to like this model called Text ADA. You can also do it to Text DaVinci. You know, in the future, if like GPT-4 is available, you can also do GPT-4. Any large language model, as long as it's like sophisticated enough, you can call to it. Yeah, and then what you can do is then you can score using that language model. What will happen is we will have like the query plus option. So the query is like whatever context that comes before, and your option is like the description of your skill. So based on this, you take the reverse of the tokens, and then you keep doing until you get like option start. So option start in this case is like an enter, like a new line, which means that that's the end of my action. So each action is separated by or each skill is separated by a /n. So what we'll do is we will then take the score of the log props here, and we will add up all the log props together. So this is basically the sum of the log probabilities of the token prediction when we run through this part here. Sorry, just to check, can you all see my code here, the SayCan robot pick place? Can you all see it on the screen? If you can, just give me a like thumbs up so I know you all can see it. Okay, yeah. So I just want to highlight how the GPT scoring is done, right? Then, of course, in order to make all the actions that the robot can do, what we do is we have this thing called the pick targets and the place targets, and then you just do like a for loop to enumerate all possible pick and place locations. Over here, the pick and the place targets are given by the environment. And okay, right now I need to scrub a lot to show it, but you can see that here, like these are the targets that you can, I can pick yellow, green, blue, yellow, and then you can place into the bowls. Yeah, so there are different targets that you can configure. This actually is a pie bullet environment. So you can put all kinds of blocks, yellow, blue, green. You want to give more blocks, you just need to put the right color code. Okay, it's at the top of the code. Okay, I'm not going to show that part because I want to focus on the SayCan part. So this SayCan part here is basically the part where the magic lies. So I just print out all the options here to just show you like what are the kind of actions that the LLM would output. So the LLM will actually output all this. Okay, so next, this part is like how we normalize the score. Like you take the max score and then we normalize it, click to 0 and 1. Okay. Okay, this part we will skip. And this is the affordance. So for affordance, they are using this VLID method. And what you can see here is only when you can find the pick object in the found objects and you can find the place objects in the found objects, your affordance is 1. If not, your affordance will be 0. Okay, and in order to discourage the done option, the affordance is 0.2 for the done. Yeah. So next up, okay, there's this thing. So I was wondering how they actually train the large language model, because you know, large language models off the shelf are not exactly trained on a robotic task. How do we train the large language model such that it can fulfill the tasks? And for the demo that they gave, all right, it actually uses few shot learning. All right, so this is how the like past few examples will look like. You give it the list of all the objects in the environment. You give the instruction that you want to do, the goal that you want to do, like move all the objects to the top left corner. And then you give all the sample instructions that the robot should do, like blue block top left, red block top left, yellow block top left. So like top left corner is actually a location that is encoded for in the environment itself. So it already has a particular XY location. So this basically tells the robot, given this meta level instruction, these are the sample like step-by-step instructions that you should. So I can tell like more stuff, like you can do like light colored break, put the yellow one, the green thing, you know, it's green thing, you see, not even green bowl, green thing. So like the LLM can generalize to bowl, okay, from just these examples. It's actually quite amazing, like sort all the blocks into their matching color bowls. Imagine programming this in the robot. It's so difficult, but with NLP, you can like give it like a few of examples like that. It can probably generalize to other semantically similar examples as well. That's the beauty of NLP. And NLP, I think, is the way to go to do goal planning, especially in reinforcement learning. So mark my words, I believe NLP will play a huge role in goal planning in reinforcement learning. So these are the examples that we train on. And then what we'll do is, so I tested, okay, I was playing with this this morning. I spent about 4 hours tinkering with this. I thought I could show you all some of the outcome, but OpenAI API like kind of gave up on me. Maybe I didn't pay, that's why I cannot use. Okay, so you can see over here, internal survey error. Maybe too many people use ChatGPT, you know? Yeah, that's why this didn't work anymore. But when it was working, I tried out, okay, I tried out like few short learning with prompts. So this part I actually typed out myself, all right? So I tried with the prompt over here. With the prompt, all right, you can do stuff like put blocks in 4 corners, move light to the middle, which is actually similar to what you see over here. Okay, but if we don't do the few shot learning with this prompt here, if we don't do this prompt, we just directly give it this instruction like that. Okay, it can only do very simple instructions like put the green block in the red bowl. Okay, if you ask it to do like put blocks in all 4 corners, it kind of doesn't really work anymore. Okay, because it doesn't really know how to do the actions without this kind of past examples. So few shot learning is quite powerful. And in this context, just because this environment is quite simple, just having a few shot learning examples can greatly enhance the performance of the robot already. Okay, so yeah, this is basically how we do it. We basically put the prompt with like the scene description is like what are the found objects, and this found objects here. Okay, the code is actually below. The found objects uses the VLID system, which basically just detects whether in the image that object is present. Okay, now we have this thing called the LLM score. LLM score uses the log likelihood or the log probabilities, the sum of log probabilities. Then we have affordance score here, which is based on the VLID. Yeah. And then what we do is you can see the combined scores here. We do the exponential of this LLM score times the affordance score. So this exponential is what I was talking about earlier, because we did a log likelihood, which is the ln. When we do like e to the power of like -4, you get back the probabilities. Yeah, so this is exactly what we are doing. So we take one probability, multiply by another probability. You know, you need not actually do probability by probability. You can also do addition. Yeah, so there's different ways of basically combining them, but multiplying them works as well. Multiplying them means that both the LLM and the affordances are IID, independent, and you can just multiply them together to get the combined probability of success. So yeah, this is just one method of doing it. Yeah, and in the end, we just normalize the score to make them from 0 to 1, and then we take the max score. Actually, you don't have to normalize, you know, because if you just take the max, regardless whether you normalize or not, it's the same. So yeah, this is an extra step. Yeah. So unfortunately, I cannot show you what's over here, but what I can do is, you know, maybe you all can just run this notebook, and then what you will see is that you will see that there's each of the different actions will be having a different score. Yep. So this is the real SayCan architecture itself. Okay, you can see that this is like this is one of the environment here. Like we have a red bowl and a few bricks. Okay, and over here the task that we want it to do is to put the blocks in all different corners. And so we run this. You can see that it's exactly everything is the same. Okay, the only difference now is I do sequential. So what the model does here, because it's a very simple environment, the model actually does the LLM prediction and the affordance for all the steps at one go. Okay, but in the real life robot, you need to do step 1, they redo the whole process again, then step 2. Here they already did all, so you have a list of steps, like put the green to this corner, put the yellow to another corner. You have all the list of steps already. Okay, and what we do is then we execute the step 1 by 1. Yeah, so this is how it's done. Okay, and at each time where we do the step, you can see we actually append, okay, the step that we chose. Okay, I think it's here. We append the previous action that we chose to the prompt itself, so that in the next cycle, the prompt will be for the next action. Yeah, so this is the part here. Okay, unfortunately, I can't show you like what happens here. Okay, but the idea is like you basically use some. This is the VLID. This is the VLID part, VLID part, where you identify what objects are there in the scene. Okay, and then from this, then we score our all 53 actions. We choose the best action based on the affordance and LLM. Then we do that for the next time step, and so on. Yeah, so you know, there's a server error here, but this is how it will look like when it's running. Like this is the first time step. Yeah. So yeah, any questions so far on the code for this? All right, so you can see that it effectively like sort of generalizes to different like input instructions or input goals just from the capability of the language model itself. So if your language models improve in capability, your robot can interpret things more dynamically and more user-friendly, in a more user-friendly way as well. So it is actually orthogonal to the developments of LLMs. As LLMs become more and more expressive, your robot will be able to understand human intent better. Okay, because the list of actions are already already axiomatic. So you just need to choose what actions to do. So it's quite cool that LLM models can actually do this kind of planning. So let's see how this fares on the experimental evaluation that SayCan uses, which is a kitchen environment. So this is like a real life kitchen. You have a table, a trash can. This is the close counter, a far counter, and so on. And these are like some chips, some gassy drinks, apple, and so on. And the robot that they use is actually the robot called the Everyday Robot, which is this robotic arm gripper with 6 degrees of freedom. Yeah, can you see the slides again, by the way, just to check? Maybe a thumbs up if you can see the slides. This experiment setup slides. Okay, thanks, Christian. So I'll skip this. So what are the kind of instructions or goals that they actually gave? So it starts off simple, and then yes, more complex goals as well. So it's like stuff like let go of the Coke can, bring me something. Okay, restock. So there's some verbs as well, like restock. And we also have like structured, like move something to something. Yeah. So it's like the various ways of encoding this. Okay. We also have like put cook on the counter. So this is embodiment in the sense that we have different stages of the robot's gripper arm with the same instruction, and then we see whether the affordance can actually cue the language model, to do something. Like for example, if the arm is like all the way at the top, maybe the first action should be put the arm down first. Yeah, that kind of stuff. Yeah. So this is called embodiment because it is related to the robot's position. Crowdsource is basically miscellaneous. Yeah, so it's like there's a random query from some user outside. Long horizon is when you have something that requires a long amount of processing steps to do, like spit my code on the table, throw it away to bring me something to clean. Yeah, so this, like, you need to throw the code can away and you need to bring something to clean. So this requires like 10 over steps. Yeah, so these are long horizon tasks. So let's see how SayCan performs on all these tasks. So these are the metrics used, whether or not the skills selected can actually perform the goal. All right, this actually is also rated by 3 humans. 3 humans will tell like whether or not the plan is correct. So based on the list of actions and the goal itself, whether or not the robot will fulfill it. So same for evaluation is not just the plan must be right, the robot must actually perform it correctly. So this again is rated by 3 humans, and these 3 humans will then give it a score like of 1 or 0, 1 for success, 0 for failure. And if 2 of them rate it as success, then the robot is deemed to be if at least 2 of them say it's success, then the robot is deemed to perform it successfully. So you can see that this part here requires quite a bit of effort in order to like evaluate whether the goal is fulfilled, right? So in actually a follow-up work, this is called basically there's a follow-up work by one of the authors that they use some form of like self-taught. I can't remember the name of the paper, I was reading it just now, but the idea is you basically talk to yourself and then you can sort of like reason. And then they also have a success predictor module where it's basically trained by supervised learning, like whether or not the action has led to a success or not. So this success predictor module can actually help to alleviate like using humans, because it's very manpower intensive if you want to use humans to evaluate every single action. Yeah, so maybe you can offload it to some neural network. Yeah, this has been done in some future work. Okay, let's see how SayCan actually does this. Okay, this is a very complicated table. And let me just highlight the key things that you need to look at. All right, so this is a table of like the success rates of like this, the mock kitchen environment. This is the kitchen environment. So mock kitchen is a simulator. The kitchen is the real one with the actual robot. Okay, this is no affordance, which means that we don't have any like RL value function. This is no value function. Okay, and this generative means that, okay, instead of using fixed actions, okay, the generative thing is again also don't have value functions, but this generative means that the LLM part is free to predict any text, and then we just match it to closest axiomatic action. So that's exactly what we are doing here for the generative part. So this is to just see whether or not, if we don't constrain the LLM to predict like the log probabilities for the fixed action, whether we just let it free flow the action, whether it can perform better. Okay, then the last part is, of course, no LLM. I think we don't have to go through this because like even with like, this is behavioral cloning with like some form of like high level mapping, users sentence embedding, something like that. Yeah, so this actually shows that all this kind of don't work. So this part here, we can just see that we can just draw the conclusion for this last part. LLMs are important. Yeah, that's the conclusion we get from this last part of the table. This affordance part, let's just take a look at the affordance part of the table. The affordance part of the table tells us that, with some form of, with no value function, it doesn't do very well. I mean, you can compare with this and this. You can see that without the value function, without the grounding by the reinforcement learning value function, it doesn't give the right sequence of actions at the planning stage. Okay, and this is not the best. All right, so we can see that we kind of need a form of value function. Okay, but this is the interesting part. Okay, without the value function, but we do a generative method to project the nearest skills. Okay, rather than just constraining to the skills that we have so far. So this is quite interesting. You can see that with the generative model, it can actually predict quite well, like 74% compared to like, so this is the planning part. It can predict quite well, but I believe this is with respect to like the mock kitchen. Yeah, it doesn't do that well compared to having both the affordance and the LLM. So you can see that the LLM itself actually, sorry, the affordance itself actually does help to increase the success rate. Okay, then we look at the main results here. The main results is that in the mock kitchen, it can do very well, 84% compared to, okay, this means it plans quite well, but once it comes to execution, you know, sometimes the robotic state kind of fails it. Yeah, same thing for the real kitchen. You can see that the actual robot itself doesn't do that well compared to the planning, which means that the actual situations are more difficult to kind of predict compared to like just having the meta level plan here. To execute it in the real world is actually quite difficult. And the main things that it fails in are actually the embodiment part and the long horizon part. So embodiment is quite easy to see why it fails most of the time, because embodiment is difficult. Okay, in order to start from different start states of the robot and execute the instruction, the robot kind of needs to, you know, reorientate itself and so on, which is something that the language model doesn't do very well. So the language model, as you saw earlier, the pick up the sponge or find the sponge, you know, it doesn't really tell the right action. It just has the high level plan. But this part where you need the low level plan, okay, you need some form of value function or some form of affordance. This affordance part, okay, is actually highly reflective in this embodiment. All right, and what this means is that the way to encode affordance is not optimal here. Yeah, we can actually do it in a better approach. Yeah, so yeah, this is one of the things that we see. Then long horizon, you can see that it also takes has also a very low success rate in real life, like 47%. And this means that, you know, I just write it here. One step look ahead may not be enough. Yeah, in order to like do this long horizon planning task. Actually, the main thing for this long horizon planning task is that the robot execution sometimes may not be the desired plan. Okay, so this something to do with the actual like low level policy itself. So overall, they did analysis, and then most of the cases of failures are from failures of the LLM, where the LLM fails to predict the correct output. If you compare both the LLM and the affordance, and 35% of the failures come from the affordance itself. Okay, what does this tell us? This tells us that most of the time, the LLM is the critical part to actually choose the skill, as we saw earlier. The affordance is like the icing on the cake. It's like if your LLMs actually predict more or less correctly, the affordance is the one that like does the final tweak. So you can see from the failure case, this is exactly what is reflected here as well. Yeah, but overall, we can see that both the LLMs and the affordance are both important for SayCan. Okay,
I have two questions here.
Yep.
First is for the planning, right? How did they evaluate the accuracy without execution?
Oh, the plan will be like based on a series of steps. You ask a human to evaluate whether this series of steps can actually solve the instruction. So it is a theoretical thing. Like if I ask you, like, I want to bring a Coke can to you. So pick up Coke can, find Coke can, pick up Coke can, bring Coke can to you, put down Coke can. Then I pass this script to you. Then you tell me, does it solve your Does it solve your goal? Then you tell me yes or no. Yeah.
Second question is, I don't understand why for the generative experiment they choose not to use affordance. I think it would make more sense if I were to conduct experiment for the generative, I would definitely go and see what's the difference between with and without affordance. Because if you don't even have a predefined set of action to ground your action, then generative can generate anything, right?
Yeah. So actually, I feel the generative option might be an interesting approach to try out in the real model, in the full model, but they don't have experiment results to show it. Yeah, but I agree with you. I think it'll be interesting to see like whether or not like with okay, so the thing is you actually can still have affordance because you see the generative thing maps it to the nearest skill, which means that you can actually have the affordance value for that skill itself. Yeah, so I agree with you. We actually could have affordance with generative models as well.
Okay.
Yeah, but I think this didn't do too well. That's why they didn't do it in the real model. Yeah, this is my gut feel. I think the generative model didn't do too well. If not, it'll be highlighted here already. Yeah. Okay, let's move on. This is just to show that like a more complicated model, like the PALM model is 640 billion. Okay, I think the FLAN is a 50 billion. I can't remember the amount, but with a larger amount of parameters, it kind of improves performance. And I don't know whether you increase the performance of LLMs sufficiently, you can actually approach the 100% solve. So this is an open question, whether a more complex LLM can actually solve the full problem, or you need something else. I'm more tempted to say we need something else, because as what we can see, majority of the failure cases come from not understanding the state of the robot. Okay. Unless your language model can have multimodal, including the robot state as well. Yeah. But the problem with that is that the more components you add to your language model, the more amount of training data you need. And LLMs right now are trained with text data of the world. They are not trained with robot like input-output data. So that is a potential issue. That's why this model of SayCan, they use a traditional text-based LLM that is already pre-trained on the world's data. Yeah. So, modularity actually helps to improve the learning efficiency. Yeah. If you want to learn too much at one go, it might take too long to learn. Yeah. So I have my reservations with like using a more complex LLM to solve the whole problem. Yeah, I think we still need more like modules. Later we can discuss more in the discussion question, like how can we help to improve the performance of SayCan, right? This is one of the works that they have done to actually improve the performance. It's called chain of thought reasoning. So instead of just having like the context or the goal and then the list of actions, what will be done is they actually train the LLM to output an explanation, like fruit flavor without caffeine. Then you can say that drink that fruit flavor does not have caffeine, and then bring the lime soda. So this actually has been done in the PALM model, PALM model, where you try to explain some form of rationale or reasoning in order for the language model to sort of pick up the right relations. All right. So this part here might require some form of fine-tuning on the data set of robotic actions. Okay, because your model itself for the PALM SayCan won't automatically, tell you like, oh, what is the drink and so on. You probably need to fine-tune for some episodes. This is not really said in the paper, but I believe you need to fine-tune it. Earlier, you saw the pick place environment. The pick place environment LLM was not fine-tuned at all. You just need to use a context prompt, and then it can already perform the job. Okay, so this is the difficulty of chain of thought. If you want to do chain of thought, you probably need to do some fine-tuning. Okay, because if you were to just use the off-the-shelf method, the explanation may not suit your use case. All right. So like over here, unless before that, you can put like items, jalapeno chips, cookies, fruit juice. Yeah, I mean, one way to do this without doing fine-tuning is you already have the list of environmental factors as a prompt as well. Yeah, so this is the beauty of large language models. Like, it can sort of like arbitrarily perform at a new environment if you just use different like context prompts. And in this case, I don't know if you all heard of Bing, Bing search. Bing search, the Microsoft one that they use some form of ChatGPT to search. Actually, the Bing search is more or less ChatGPT, except that they put like some list of rules for ChatGPT in order to optimize for search. Like the results must be relevant and so on. So people have done some prompt attack, and then like they figure out that like, not sure how true it is, but they figure out like for Bing search, the AI is called Sydney, and then it's given like a list of rules to follow, and then just using that as the context, it can already generate like search already. So similarly for this case, perhaps if we give it the full context, the model can already generate the explanation using a few shot learning, all right, even without being explicitly like trained for it. So either way, the explanation is generated by the LLM as one additional pre-training step. So the LLM will generate the explanation. Explanation will then be used the SayCan method to generate the actions. Yeah, so it's one extra step, but this actually showed that I think it improved performance by 5 to 10%. Okay, results not in this paper, but results are in the other paper where they use like the self-reasoning paper.
Sorry, question. So the robot here is like who is
the same robot? It's the kitchen robot.
How is the robot able to generate? Sorry, are these generate prediction or these are the action taken?
These are the actions predicted by the LLM.
No, but you just mentioned the explanation is also generated by LLM.
Yeah, the explanation generated by LLM.
What about the robot?
And the robot doesn't have an explanation. The explanation is in the language model.
How is this sequence of action? What are those things? Are they action or are they the prediction?
These are the actions that are generated, like the skills, and then later the robot will then execute this.
So you have two different language model or what? I'm confused.
It's the same language model. It's just that now they have an extra explanation line here.
Who is the one given the explanation?
The language model will predict the language explanation itself, and then they will add it to the original prompt. So this is the original prompt at the top. The language model will generate the explanation. They append the original prompt plus explanation, and then use it to generate the actions.
Use it to fed into which model to generate the explanation?
The same model. So it will be the PALM model, PALM model.
So you are okay. So you human give a task first, then the language model generate the explanation. Then you fed this explanation again to itself to generate the action.
Yes.
Also, you are feeding the output from itself to give it again to generate a set of.
Correct.
Oh.
Yeah. So the benefit of this is that the explanation can help to bias the actions chosen. Because like over here, they already say I'll bring the lime soda.
But this is not the intervention from external environment, right? It's just its own explanation. How do you bias it?
Yeah. This is only the LM portion.
No. So my question is, you are using some explanation given by LLM trying to bias its own action selection. It doesn't really make sense to me.
I mean, in some sense, it is a way to like provide some form of lengthier prompt in the hopes that the model can reason better.
Yeah, but the prompt is not from external, not from human. It's from the model itself.
Correct, but the model can do few shot learning, you see. So with few shot learning of some human labeled examples, perhaps it can already generalize the context.
Yeah, the way I understand chain of thought is you need to interact with the model to guide its output. Not
that's for input-output relations. Yes. So I was thinking for this chain of thought reasoning, it will be perhaps difficult to do few shot learning, maybe you need to fine-tune this. You need to use this as a way to fine-tune on the PaLM model. So this is not stated in the paper, but I believe if you were to do like a few shot prompt engineering, the explanation may not be ideal because like you may not have the right context. But again, I might be wrong because, you know, this kind of language models, they are very versatile. You give it a few examples, maybe it can generalize already.
Okay, put my question another way. So if the model itself is able to provide the explanation, right? Then surely it can just generate the output action.
Okay, so you are saying why not we skip the explanation step, right?
It's the same thing because you are not like doing any intervention with the model, right?
Yeah,
so if you generate explanation, then you don't touch it. Then it just use its own things to feedback to itself. Then you generate action. Then what's the point?
Okay, let me explain it in terms of like how a human would do it. All right. So if let's say I don't ask you to generate the explanation, ask you to generate actions, you may not think of this explanation yourself. But if let's say I put in the question, like for example, an exam question, give me the rationale of doing this. Then after you write down the rationale, you might already think to yourself like, oh yeah, this is the rationale I want. Okay, then from this rationale, I plan the action. It's something like a priming method. Because
is it the thing like just now you like talking to yourself, the thing just now you mentioned self-talking or self.
Yeah, self-thought, yeah, self-dialogue. I have to find the paper name again, but the idea is use the model to like generate some of its thoughts. And then from that thoughts, you can then use it to like correlate to find the next action.
Interesting. So you don't need any external intervention, or that can improve.
Yes.
I can refine it. Okay, that's quite interesting.
It is a priming method where you prime it to think or prime it to give reasons. And then because of the reasons it comes out, it gets more accurate at the next step of prediction. Yeah. So I think this also applies to humans in some sense. Like if I don't ask you to think of certain things, maybe your answer would be different.
I agree, but here you can, if there's nothing happen in between explanation and the action generator, right? Then it's just simply auto-regressively predict the next.
You're right. You're right. So in this case, the hopes is that this LLM will have learned from other examples that can generalize to this example. Like for example, without caffeine, it might have learned like these are the drinks without caffeine from somewhere else. And then based on the context, it can like generalize, okay, lime soda is the only one without caffeine in this scenario. Yeah, so it's the hopes that because this explanation, if you want to train like that to like that, is probably not a good idea because you can see in terms of information theory, right? Information theory, the explanation has actually more information than the prompt. Yeah, usually we cannot do this kind of thing. We cannot learn a more detailed explanation of something less detailed. Information has to funnel down from a lot of information into fewer and fewer information. That is how information theory works. The more
you're talking about the data processing equality, is it?
Correct, yes. So the more you change your initial data, the less information you actually have. There's no way to get more information from a fixed pool of information. Yeah. So if you talk about this information theory kind of view, it doesn't make sense that your explanation can be more detailed than your prompt. But you are forgetting that these language models are trained on a lot of data sets, even more than just this robotics thing. So it is with the hopes that the extra other data sets that is trained on can help to provide this information that this robotics system is lacking.
So okay, but then like for example, if it already give you the explanation, right? Then why wouldn't it just continue to give the next line on the action? Why you need to append it, then input it again back to the model?
Okay.
Still doing auto-regressive prediction.
Well, it's just the way language models work. You know, if you don't put the word, you don't put the word explanation here, the model might rattle off something else.
Right.
Yeah, but if you put the word like explanation, then it knows, okay, I need to explain. Then I will come out with the explanation.
But do you put the word robot there?
Okay, then this robot here, no, you don't put that. Okay, what will happen is that you will do the same way as what you did in the SayCan model earlier. You just append. Okay, maybe you can put the word robot here. No problem. Yeah, I don't know how they train this chain of thought. because it's not ready. But then what you do is you do the LLM and the affordances for each of these actions. So these actions are not generative in nature. These are already fixed actions. You are then calculating the score for each of these actions, and you pick the best score. Yeah, but I think you are right here. Like, why can't we generate the whole thing in total? It's because of this part here. This part here is constrained. If we don't constrain this part here, we can probably generate both the explanation and the robot in the same step. But because we are constraining this action generation here, we need to evaluate all possible actions and then pick one of them. So this is actually like an additional step other than the LLM. You also have other like mechanisms to consult. That's why this part here
I think there might be something happening between the explanation and robot. Yeah.
No. The explanation to the robot is the same as the SayCan method I was talking about earlier.
Okay.
Yeah, is that diagram that you saw at the first slide. I can refresh the diagram again. Is this diagram? Yeah. Okay. So over here we have an extra thing called explanation, which is generated by the model itself.
Sorry, I forgot. So how do you constrain the output just to those few options?
You just evaluate the scores for the LLM and the value functions only for all these actions at the center.
As in, then how do you even let it to output exactly this set of action in the first place?
It's predefined. You have to user input define the actions.
Through in-context learning or?
Right now, is based on what the robot can do. Like this.
No. Do you how do you tell LLM to only output this set of action? That's my question.
Oh, you don't. What you do is you will put this find an apple as the output prompt itself, and then you will calculate the probability of predicting the word find, which is maybe like 0.1, the probability of predicting the word and, which is like 0.2, maybe apple is 0.1. You just take the log probabilities and you add it up. So it is a force. You basically force the LLM to output these tokens, and then you just use the output layer to find out what's the probability of these tokens you output. You get what I mean? It's not a free flow kind of generation. It's a forced generation. And then you take the LLM's output layer to see what's the probability of the tokens that you just predicted.
Okay, maybe let's continue.
Yeah. But yeah, thanks for asking these questions. Yeah. Okay, I think I want to give some time for the Q&A because this actually has a lot of relevance to like the methods that I have here. But I need to use the toilet for 1 minute, so I'll be back in a while. Yeah, give me a while. Hey, thanks for waiting. Yeah, I'm back. So let's spend the last 10 minutes concluding this, then we go to the discussion because I'm going to spend some time in the discussion. So this is the reason why I chose this paper to think about today, because I was thinking more of like, how can we do meta planning, okay, using like a goal state, and this goal state can be written in natural language processing, and then how can we come up with the like sub goals in order to like execute. So in some sense, like if you look at this a path towards autonomous machine intelligence, you can, oh, I'm sorry, just to check, can you hear me? Because I just came back. Can you hear? Okay, yeah, thanks. So this one can be something like SayCan. SayCan can do the top level planning, and then outcomes like actions like pick up the sponge, bring the sponge to you. Then you have low level systems that can actually execute this these orders, okay? Like over here, in order to pick up the sponge, maybe like robot arm to certain XY, you know, activate gripper, you know, these are like some, in fact, you can even have even lower level things like robot arm go down here. You can even have stuff like actuator moto 1, move 3 juice left, you know, that kind of thing. Moto 2, move something like that, you know. I mean, it can even be planned at an even lower level. Yeah, so the idea is that you have a high level planning, low level, low level. And the highest level here has to do with some form of natural language processing, because it's been known that we actually think a lot in terms of language. The language actually shapes the way we behave. And in some sense, in our brains at the top level of planning, there's some form of language that shapes our actions. Yeah, because if it's not really describable by language, it's very unlikely that you can actually do that particular kind of goal setting. Yeah, most of our goals are related to our language. Like I think they did a study with some tribe before, like they don't have a notion of like I think they only have a notion of forwards and back. I think they only know how to do forwards or something like that. Then they cannot think backwards. There's a study, I can't remember what it is, but language kind of helps to shape your behavior. So I believe at the top level is some language, like what SayCan is doing. And then you come out with some like actions at the bottom level. So the fast and slow architecture that I was actually thinking about recently, there's two ways that you can link to it. First is that this part here is a natural language processing goal that can be in the form of a clip vector. Yeah, so it can be a clip embedding where you actually express like a goal in terms of like a particular vector, and then you can then use the neural network to like kind of predict the action. All right. The other way I was thinking that this could actually be used is that maybe this fast and slow is somewhat related to the LLM and the memory. So like this neural network predict the action. This could be some form of like using so instead of like using an MLP, over here I use MLP, but instead you can just use large language models to select your action that can also condition on the prompt, which is your goal. Right? And over here, this can be a very fast way to say feasibility of attaining goal. So, earlier on in the paper, they talk about Q learning, right? But the Q learning is like takes 100+ hours. What if we could state the feasibility of the goal just from referencing past memories? So like if you reference past memories and see similarity of the current state, yeah, you can use that as a proxy to see like whether or not it's feasible. Okay, the other way that we can do it is we can see whether there's a link of based on a certain action, there's a link of like based on the list of potential transitions in your memory, you can reach the goal state. So if you can sort of find a transition of states all the way to the goal state, okay, using your memory, you can then put this as a high kind of feasibility. So somehow this memory retrieval architecture could be the way to determine whether or not it's feasible. Like for the robot arm, that kind, like if you see nothing of a sponge in your image, then in your memory, you cannot really do the pick up the sponge action, right? Because there's no sponge to pick up from, there's no state to transition from that memory in your head. So rather than just kind of using Q learning, which takes very long to train, we could just approximate like your feasibility with like some form of memory selection, like whether it's similar to memory. This is like for single state. And then if you want to do like multiple state look ahead to your goal, you can use this sequential look ahead mechanism. Yeah, of course, how to abstract the memory, that is something that needs to be discussed. I think Shucha and I talked quite a bit about it in Europe's. I just haven't got to implement it. Yeah, how to abstract memory well. Yeah, those kind of stuff. Yeah, so this is what I can think of like for future work. And that's why I like SayCan a lot. SayCan is a model that shows that you can actually use natural language processing to plan arbitrary goals. That is very interesting. Yeah, interesting to see whether it can work for this kind of my kind of architecture. Also, another interesting thing that it can work for is perhaps, you know, this whole craze of using ChatGPT for search. How can we get ChatGPT to output stuff that can actually be linked to an actual source itself? So, you know, ChatGPT likes to give like nonsense response sometimes. That's one. But what if you can ground your responses here? So of course, you kind of need to like know what the potential output here. We might not be feasible because like there might be so many different actions that you need to try out, like so many different sources. But suppose you find a way to actually make it feasible, you can actually then use the language model to score like how likely this like maybe you can search through a memory bank, how likely this is will fit the output. And the value function is like whether or not this is in the memory bank or not, is referenceable. So how similar is like this generated output to your memory bank? So one way is to like, I think for Reliable GPT, one way is you start from the memory bank and then you go leftwards to pick up the most likely one. So you can do it both. You can do it this way, start from memory bank and then find good language, find good response based on LLM. Okay, but I think for like Reliable GPT, you might need to do it the other way also. After you do this, you kind of need to, from this part here to here, from LLM, find out how similar, or in this case, from multiple generations, yeah. So I believe if you want to do this, like do reliable search, you need to do it like that, and you just need to keep iterating these two processes until you converge. Yeah, it may not be just a probability multiplied by another probability, because you know you kind of need to do things iteratively. So it has some semblance to maybe like stable diffusion where you like iterate iteratively. Yeah, so maybe you have to do something like that. So eventually the output is both plausible to the LLM and also highly linked to your references stored in your memory bank. Yeah. So these are just some ideas I have. Okay. So yeah, I think that has been an interesting like topic today. Let's talk about like the questions that we want to do the discussion. So the first question, and the most important question actually, in my opinion, is that we only consider actions that are finite in number. How do we program in unlimited amount of actions? Because you know sometimes there are just so many different objects you can do, like pick up a sponge, pick up the scissors, pick up a pen. You know, there's infinitely many objects and infinitely many situations you can do, actions you can do. How can we add this to the model? Okay, because if you were to do this to the current model in SayCan right now, it will explode in time complexity, because you know you need to evaluate the probabilities for LLM and affordance for every single action you consider. So yeah, I open to like discuss. You all have any ideas? How can we add in actions that are unbounded? Like, okay, so maybe I answer this question. Okay, then you all can discuss. Okay, someone message. Let me see. Zero shot help. Okay, Christina said was zero shot help. Okay, so this one is more of like how you generate out the actions, not so much on how you train the model. So one way I can think of to do this is LLMs can generate unbounded amount of text. So as what Zeri said, why don't we just use the LLM to generate, right? Why do we fix it? Okay, my gut feel is that the generative thing failed. Okay, it didn't work too well. That's why they fixed. But what we can do is we can just generate the number of actions. Okay, we can sample like X number of possibilities. And then if you want to ground it to the actions that you have, okay, then you just just basically do similarity mapping to nearest possible actions. Okay, and then you just pick action with most number of occurrence. So in this case, you don't bound your number of actions to like the list over there. You let your LLM freely generate all your actions. Okay, but in order to do this free generation of actions, what must be done is you need to fine-tune LLM to the robotic model itself. Okay, so that the actions are related to the robot. Okay, because if not, what will happen is that you will have a lot of actions that are not related. You know, like the first slide that we showed, like I spilled a drink, can you help? Then like, oh, you could call a cleaner, you could use a vacuum cleaner. You know, if you don't fine tune to the environment itself, your output is going to be very, very generic. It's not going to be the kind of actions the robot can do. So you need to do a lot of effort to fine tune. If you want to do like a few shot learning with just the prompt itself, probably the best way is to just like evaluate the log probabilities for fixed actions, like what they did in this paper. But if you want to create this model for like a larger environment with unlimited actions, you're going to have to use some form of maybe you can use the LLMs method to generate the actions, but you need to fine tune quite a significant amount of time. You need to spend quite a significant amount of time fine tuning your LLM to that particular environment, and you know, yeah, that could cost resources because you need to generate. But the thing is, after you fine tune the environment, you can just do sampling. You can just sample the LLM and then you can use that to get action. And this similar thing is used in the Meta tree search. Is the one by Meta, hyper tree proof search. Yeah. So because the number of operations you can do in the lean programming language to like hyper tree proof search is to use like a form of AlphaZero kind of search in order to solve like mathematical Olympiad questions or math questions. So the number of operations you can do is infinite, but what they did was they actually sampled from the LLMs. So maybe we could do something similar for SayCan. But the only issue is that you need to do this first step here, which might be time and money consuming. Yeah, so this is important. Okay, any other inputs for this first question? Okay.
Hello, can you hear me?
Yeah, I can hear you. Who's that? Sorry, is it?
Yeah.
Okay, yes.
So how do you, if your output action space, you're also like infinite, how do you do things like measure which action is the closest?
So if your output space is infinite, what you can do is then you can just map it to, okay, so even the nearest possible action, if it's infinite, you may not be able to compare to every single action, right? Yeah. So what could be done is that you just I don't know, maybe in this case there could be a way to like tell you whether or not the action is possible. I don't know, affordance maybe in this case. Yeah. So this is an interesting question. Like, how do I compare the cosine similarity if there's an infinite amount of things to compare to, right? Yeah. Or you just have to trust that the language model outputs valid actions all the time. Yeah, this I have no answer to. Yeah. I guess you can trust that the language model outputs a valid action. Yeah, because there's no way to actually, yeah, you're right. If there's infinite amount of actions, there's no way to do similarity mapping. Yeah, I didn't think about that. Yeah. Yeah, which means that you need to fine tune the language model a lot more. Yeah, because there's no way to it's very difficult to actually tell whether an action is valid just by, because there's no way to do similarity mapping to an infinite number of actions. Yeah. So you got any solution to that? Because I kind of agree with what you said. Yeah.
Yeah, I don't have. That's my question.
Yeah, thanks for pointing it out. I think it's true, which means that if we were to do a generative kind of model, okay, right now in the paper, they did a similarity mapping to the nearest action for the generative part. It's because we have fixed number of actions. But the moment your action space is infinite, you can't do this similarity mapping anymore. So
How
then
about
you
if you, sorry, how about if you fix the number of actions? So finite number of actions, depending on what the robot arm can do. So if let's say your robot arm already only can do pull, push, I don't know, squeeze, pick, drop, then you just fix it as that lah. So you don't really make it infinite in a sense. You have to make it finite lah, I think.
But
I mean,
if
even for the human arm, it's also finite, right? The number of actions that we do. But as in, that's what I'm trying to say. Finite number of actions.
Yeah, I guess the basic level of actions can be finite. Like
correct.
pick,
But
paste.
correct. But if let's say pick apple or pick orange or pick something else, right? Then you constrain it based on the question that the human inputs. Like for example, the human says, please pick an apple. Then the language model, first your action pick is being constrained, so that's finite. But what it is picking, right? This one maybe you can do some kind of filtering or similarity comparison to the language model. So apple versus orange versus bananas, which one is more similar? And then you don't know, shortlist from there. Some kind of filtering step.
I quite like the idea of filtering. So like your basic level actions are fixed in number because there's only so many skills you can do, right? But it's the thing that makes it infinite is the number of possibilities of performing those skills on, like pick apple, place apple, pick scissors, place. I mean, the objects can be infinite. So one way to do it, as what you said, is to constrain the number of actions, the fundamental actions, and then you filter based on context to generate like maybe another list of actions. So we could still perhaps do a like list of actions like what they did here, but this list of action will be refined each time based on like the prompt or based on the context. Yeah, so you don't do for all kinds of objects. You only do for like objects that you can see.
Yeah. Okay, anyway, thanks for the presentation, but I really need to drop off now. It's very interesting. Yeah, so you guys enjoy the discussion. So I need to drop off first. Thanks, Chong-Ming.
See you. Bye-bye.
Okay, bye-bye.
Okay, so anything else to add for the first one? If not, we'll move on to the next question.
Actually, I was thinking, how about using similar things? How they deal with continuous action in the typical RL in the first place.
How to do continuous actions here, is it? Yeah, in this case, the continuous part doesn't come into play because we do not do these actions at the low level. Like what rotor, move, what angle, all this is not in this action list. These actions are more like the higher level actions.
Like you don't think from individual action perspective, you think from the distribution of the set of action.
I mean, yes, we kind of do some form of distribution here because we find out the probability of each action based on the LLM and the affordance. Yeah, talking about action being in a continuous space here, is it?
Yeah.
Yeah, I don't think that's required to model, because like at the high level, your actions shouldn't be in a continuous space. It's a bit hard to quantize, right? I guess at the top level, what we are thinking of is more like some form of like pick A and go to B, the kind of actions which are like structured in some sense.
Okay, let me think about it a bit more.
Yeah, and also I was also thinking like whether you can use this kind of thing to learn low level actions. I mean, this one question that I didn't write here, but I was thinking about it also. Can the SayCan model be used to learn the RL policy directly? Okay, and I have this feeling that you can't, okay, because this doesn't work for continuous actions. Like it's just not possible to evaluate your probabilities for infinite amount of actions. So you have to use another kind of architecture to learn the ground skills, to learn the RL policy, which it's not this method. Yeah, you have to use traditional RL methods or some variant of it. Yeah. Okay, that's all for the first one. Let's just move on. So the next question that I have to ask is like, is the LLM itself too complicated in architecture? Because if you want to use like pick the next action, what we can do is we can just do like something similar to like what I have in like this part here, you could just actually just use like an MLP or some like MLP, ResNet. Yeah, do we really need a language model? So this thing here is something to think about, because like for example, for the pick place, you kind of only have a few bricks you can pick, a few places you can place to. You can just do it in the form of like a softmax for the number of actions. Okay, but this only works if you have like a fixed and limited number of actions. Okay, if we have like potentially infinite actions, then the LLMs might come into play. So the benefit of using this kind of models to train, okay, is that if you can use like the LLMs in order to do a vectorization here, so you can do like a text vector for the stick and another vector for the goal. Yeah, you can use like the LLMs for this part here to do the processing. So like this part here, you can use the LLMs for processing. Yeah, the actual part to actually generate actions, maybe you don't really need the LLM over here. Okay, why I say so? Because actually to train the LLM, because of the number of parameters in the LLM, it actually requires a lot more effort, a lot more iterations in order to train the LLM properly. Like if you use a larger model, you need to train with more examples as well. Yeah, so in order to like make it more concise, maybe the LLM part could just be the top part here. And then like when you actually map it into like a latent space already, you can then use like a simple architecture to predict the action. That's if you have a finite amount of actions. So yeah, I was just thinking whether or not that makes sense. But yeah, you have any comments on this?
I think it depends on what kind of task you want to solve.
Okay.
If you need something really requires something akin to human common sense, you have to use a large language model. I feel.
Yeah. If your actions are like potential combinations of different things to different things, I think LLMs are probably one of the only ways to do a generic response. Yeah, which also means that it's tied down to the first part. Like we should probably do the unlimited amount rather than the fixed actions, because if we do only fixed actions, then I think LLMs are a bit overkill, in my honest opinion. I think LLMs are used when the actions are infinite, usually. Yeah. Okay, so let's move to the next one. Currently, model only doing one step look ahead because it uses some form of a probability function from the LLM and the affordance. How can we solve long horizon tasks better? Okay, so this one, actually, I was thinking about this. And one way I can think of is, unfortunately, tree search is a way that definitely it will help to look ahead in order to like look at the future possible states, and then you can use it to see whether or not like the future state is better or not. So you can use like Monte Carlo tree search and so on. The only difficulty about this is that you need a good world model to predict. Okay, which is difficult because in the fast and slow, I also investigated world models take very long to be trained. So maybe we can do like a variant of it, tree search using memory mapping. Like you can map based on your previous memory, like what you did, and then you can change the world model according to that memory. So tree search is definitely one of the ways that we can do better for long horizon tasks. Another method that I can think of to do better, and this one Chu Sheng would like it a lot, is called chunking. So like, or hierarchical planning. Like you can actually, if you can do like pick sponge, find sponge, pick sponge, bring sponge, this one can all be classified under one action called get sponge. Yeah, if you can sort of plan at an even higher level where you have groups of actions chained together as one meta action, you can actually use fewer planning steps, because like all you really want is to get the sponge. So it's like, if I want to clean the spill on the table, what must I do? Clean spill, what must I do? Get sponge, clean the spill. That's all, 2 actions only. So so in the SayCan architecture, they have to like find sponge, pick sponge, bring sponge, use the sponge, go on the table, and the robot can even use the sponge to clean it. So if you can have the actions at a even higher level, you can do less look ahead. And so this whole idea of hierarchical planning is quite interesting, because you can use hierarchical planning to reduce the complexity of your planning And if you can chunk them up in the right way, you actually can solve more tasks because you can use fewer look ahead steps to solve it reliably. Yeah, so these are the two things that I can think about to do that. Yeah, you all have any other things to chip in? Okay, if not, let's go on to the next one. Can we use something other than the value function to score affordance? So you all saw that the Q value need not be that great. So one way, like what they did was to do approximate by vision, like they use the VLID method to find out what objects are present in the scene. So that's one way to do it. Okay, but ultimately the main thing is that you just need to have high affordance for actions that are feasible and low affordance for actions that are not feasible. How you do it is entirely up to you. Okay, it's up to the system itself. And in fact, I was thinking like even to score affordances, you might be able to use like the memory system to find out links of memory to goal state. Yeah, so perhaps something like that could be used for the finding out the value of the affordance as well. In the fast and slow system, the slow system could also be used to score affordance as well. So yeah, that's you have any comments on this?
Why do you think the value function is not a good way to go about it?
Oh, because for one, the value function requires like over 100 hours to train, and like it is basically not very effective in terms of finding out like whether or not it can solve the goal, because it depends a lot on like the value being able to back propagate from the end state to the current state. Value function itself is a very slow way to train it. So
but the current architecture, it resembles a lot of the actor critic RL kind of paradigm, right?
We can use actor critics. They'll be much faster to train, but they still face the same issue in the sense that you will still need to use like a lot of episodes in order to train your actor critic architecture.
But now it's better because we don't need to train the actor.
Don't need to train what?
The actor, because the actor now is LLM.
Sorry, I hear you distorted. Can you say that again?
Here our actors is LLM, right?
LLM vectors, is it? No,
So
this
we
is
don't
not
need to train the actor.
This is the value function. Oh, you mean the actor part of the actor critic, is it? Yeah, no, so this method didn't use actor critics. They used the temporal difference learning with the Q values. So that's why I say it's slow. But okay, yeah, I think what you're saying is that maybe actor critics can learn faster. So I give it to that. Yeah, maybe it can, but still we link to the last question, all right? Actor critic methods actually don't really solve very well tasks that are unseen. Okay, they tend to solve like unseen tasks, like dynamic tasks. You kind of need other ways to do it. And one way is like large language models can actually help to solve unseen, because like they can use context, they can use learned experience elsewhere, learn mapping, learn associations elsewhere. So large language models can actually help to do it. Yeah, you can also use like CNNs or like image models, because they can actually map to unseen images if your filter is correct. Yeah, so this is some ways to do some form of extrapolation. So I think this one already there. Yeah, the other way that I can think of to like solve this unseen task is perhaps to use a way to like map previous experience to novel ones. Yeah, so this one can be some form of like a memory system, or it could be something like you can do a more high level planning. Okay, because the higher you go, actually the more generic your plan is, and the more mappable it is to like different scenarios. Like if I ask you to find a sponge, right? And like the sponge can be in a drawer, the sponge can be in a cupboard. Yeah. So like if you can fulfill the action called find a sponge at a higher level planning, at the low level, you know, as long as you can get the action done, you can solve this unseen task already. So yeah, there are various ways to solve this dynamic problem. But the key idea is, I believe, to find out, like, actually all you can see here is like, there are two key things to do. One is association. So association can be using LLMs or memory. And the other one is actually this CNN part. This is modularity or inductive bias. If you have the right inductive bias or modular architecture, you can train on one kind of different scenario, and then you can generalize to a lot of others if you use the right inductive bias. So yeah, this is more of a question of what are the kinds of models you are using, rather than the SayCan architecture itself. Because the SayCan architecture, the beauty of it is that it can take different components and you can mix and match them together. You can take the LLM component and you can put in there. You can take the actions from your robot and you can put it in there. So it's like quite a plug and play system. So that's the benefit of that. And the LLMs can extrapolate quite well. I mean, like, it's not trained on the system, but it can sort of infer what the system requires just from language alone. So yeah, I think this architecture overall, the SayCan architecture, is quite interesting and definitely something that should be worked on in order to build like this kind of hierarchical planning systems. Yeah, like this kind. Yeah. So yeah, maybe I'll just end on this note. Any other things that you'll like to talk about before
I have two comments on two of your comments earlier.
Okay, sure.
One
Okay, sorry, your internet connection I think is quite bad. Maybe you want to type it out in the chat, then I will answer you on.
So just now the experiment case out offline.
Yeah, sorry, I actually hear you quite distorted. Maybe you just type in the chat, I will answer. Or discuss offline. Oh, yeah, sure. Okay, so this is definitely a very interesting architecture, and I think this is something we can use to do like generic kind of application of learned skills. So actually I got two more slides here. This is like the clipboard architecture, but like you can use the language and then you can guide the like kind of actions to do, and like the affordance classifier using some form of like image with a pre-trained text encoding. Okay, so this is just extra slides. Okay, but I like to end here on this. Maybe I end on this slide. Yeah, so I do believe this whole SayCan architecture is a very simple one. This gives it flexibility. This one gives it like grounding on whether the action can be done or not. So both of them together, and then you can do it in terms of a sequential planning. Both of them together has a lot of plug and play components. You can plug and play the language model, plug and play your action. You can even plug and play your value function. You know, there's a lot of things that you just change the component and the performance will improve already. But the idea of using a flexible architecture with a more fixed one, okay, like flexible as in the LLM, and the fixed one maybe is like task affordances, because this tells you what is feasible. So in fact, if we put in Dan Liang's idea of like filtering the potential actions, we can actually do a filtering of the potential actions here, generate different table based on context. Yeah, we can even do something like that. Okay, and we can make it very, very generic. So the whole system itself is quite interesting. And the key thing here is also this idea of hierarchical planning, where you already, with learned skills. This is very important, because if we need to train end-to-end a system like reinforcement learning from the high level to the low level, it is almost impossible to train it. So maybe we can take some insights from this method, okay, train skills in a modular way, and then use a very generic architecture like LLM in order to map learned skills to new scenarios. And maybe that's how we get like general AI. Yeah, so this is a very interesting approach to do things. and I like it a lot. Yeah. Of course, there's a lot of things that can be improved on, like how to do like more infinite actions and how to, you know, make your task affordance better. Yeah, these are, and also LLMs is how to make them more able to understand intent. All these are interesting future directions. But overall, because this architecture is so flexible, you can just combine them in a plug and play manner, and it can improve the performance already. So this is a very interesting architecture, and I think something like this would be the future to our AI systems. Okay, I'll end it here. Yeah, thanks so much for coming today.